Hello all, in this video we are going to see about edges. In previous video we have seen about points and patches. Point is referred as a isolated pixel or a very small region, and edge is a set of pixels. Edge is nothing but a set of pixel where the intensity changes abruptly along a line or curve. Let me show you. In the previous one we have seen this image, right? Hope you remember this. Consider this image. We have three patches. First one is sky, and second one is the mountain bed, and third one is the height of the mountain. So when you see this image, there is no edge. It is completely plain. When you see this, you have some edges. So between this line, this is blue color, this is somewhat white color, and there is a color change. If you note down this edge, there is a color change between the images, right? So that is known as edges. The intensity changes abruptly along the line or curve. When you take the second image, it is a mountain height. Here the color was different. Here the color was different. So when you consider the pixel here, we could see some other value. When you consider the pixel here, you could see some other different value. So there is a sudden change. In case of sky, there is no much abrupt change. So edge is set of pixel where intensity changes abruptly. That is known as edge. So here we are going to see about two process. One is edge reduction and second one is edge linking. In this concept, we'll see only about these two, edge reduction as well as edge linking. So edge reduction is the process of identifying the points in an image where there is a sharp change in intensity, color or texture. These points correspond to object boundaries. As I said earlier, these points are the object boundaries or surface makings or change in illumination. So why we need to do detect the edges means it represents the structure of the scene. If your image is completely blank, there is no scene, right? So the edges are the heart of the scene. It will determine the structure. So it is most useful for the tasks for object detection, recognition, segmentation, so on. So now we are going to see how to find the edges. So in case of edge, we are going to find the steep slopes. Steep slopes means abrupt change in brightness or any other colors or textures. Okay, steep slope. In case of sky, there is no much abrupt change. That is not a steep slope. And if you take a image of mountain, there is a sudden change from this part, this color to this color. So that is steep slope. I am going to identify the steep slope. Whenever there is a steep slope is there, we could say that image is having a edges. So mathematically, we can define the slope as well as the direction through its gradient. Gradient, we are going, first step is we are going to find the gradient. Gradient means I can have both magnitude as well as direction. Magnitude as well as direction. So direction means it could be of the edges or not always follow the same way, right? So the edge may be of some shapes. So I need to find the direction as well as I need to find the value of that edge also, and that is known as gradient. On applying the gradient directly would result in noisy as well as fragmented edges. Fragmented edges means the edges would be broken. So first step, I have to apply the smoothing and then I have to apply the gradient one. Okay, so smoothing means I'm going to take a Gaussian filter. The Gaussian filter is most preferable because it is circularly symmetric as well as it is easily separable. So symmetric means it can take all orientation. It can take all orientation or many direction will be applicable here. Separable means I can filter my image into either row wise data or column wise data. It can be divided. So Gaussian filter is most preferable for smoothing. This is the Gaussian filter formula, 1 divided by root of 2 pi sigma square e power minus x square plus y square divided by 2 sigma the whole square. After applying the Gaussian, and I can take a first order derivative. So first order derivative, this I represents image, this G represents Gaussian, that is nothing but smoothing, and this delta represents first order derivative. Okay, so this results in a edge reduction. After computing this, we got the edge, but they are very thick and blurred, very thick and blurred. So I am going to perform a non-maximum suppression. Non-maximum suppression means I'll consider my two neighbors, and if the current pixel is not the local maximum, the local maximum means that should be the better one. Okay, so you might remember about the hill climbing algorithm in machine learning. We'll start with a random pixel. My goal is to reach the top of the hill. I'll check with my neighbor. If it produces the result which will achieve the goal means I will move to the next point. Okay, if the neighbor doesn't reach, it doesn't help to reach the solution means I will omit that. That is local maximum. Okay, so assume that is your hill. The goal is to attain the maximum point or global maximum. So I'll start here. I'll move next. I'll move next. I'll move next. I'll move next, and finally this would be the maximum point. If the point this I move in this way means I may not attain the maximum position, so I will not prefer this way. So similarly, I'll compare my two neighbors. If the current pixel is not the local maximum, I'll not consider it. By omitting so, I can reduce the thickness to thinness. This will result in thin one. So I like to conclude. So far what we have seen means, so edges is a set of collection of pixels. Whenever you find the image, you could see multiple edges. Edge means before the line, before the edge, we could see some other color. After the line, we could see some other color. So that is known as steep slope. There is a sudden change in color on the same image. It's known as edge. We need to identify that line, that is known as edge detection. We can apply directly a gradient to determine the edge, but that would result in a very blurred or fragmented edges. So we are performing smoothing and then we are going to apply the or we are going to find the gradient. In smoothing, we are going to consider Gaussian kernel. After applying the Gaussian kernel, we are applying the derivative, but that results in a very thick edges. In order to reduce it to thin, we are applying suppression. I am comparing my neighboring pixel. If my neighbor produces a good result, I will move to the neighbor. I'll consider that neighbor and then I'll move ahead from that neighbor. If not, I'll omit that neighbor and I'll consider the next and next neighbors. Right. So this is what non-maximum suppression is. Now, after finding the gradient based detectors first use the first order derivative and require non-maximum suppression. But if you use the second order derivative, I can produce as a thin edges without suppression. That is known as Laplacian of Gaussian. Okay, so this is my formula. When you compare this derivative of g of x, here I can take a second order derivative. Second order derivative can directly produces the thin image, thin edges. There is no need of explicit suppression here. Here it follows a zero crossing. Zero crossing means after performing the smoothing, you will have certain mathematical value that representing the pixel. On applying the second order derivative, the result could be changed. It is a mathematical formula. After applying this formula, the result will be changed. Maybe this one might be changed to -8. This two might be retained as same. 10 could be minus 100, so and so. I just randomly took this number. So after applying the second order derivative, some values are changed. So positive is changed to negative, which means the positive and negative in between will have a zero. This positive is crossed to be a negative. So it has crossed as a zero. So if there is a sign change, then I can conclude that is the edge. If there is no sign change, then there is not edge. It aligns in the same way. So if you take the sky image, if you represent it in a mathematical term, all values are same because there is no change, no edges is available. If when you apply the second order derivative, I'll find the same positive value. I won't see any change of sign. But if there is an edge in your image, on applying the formula in this area, there will be no change. On applying the formula in this area, there will be no change. But if you apply the formula exactly in this pixels, there would be a sign change. So I am considering that as my edge. So there is Laplacian of Gaussian. One drawback is that it is computationally expensive. So I am going to take difference of Gaussian, that is DOG. I'll take two Gaussian filters here. First Gaussian would be of small size or large size, and second Gaussian would be of large filter. I'll take the difference of both. This result would be much more similar to Laplacian of Gaussian, and it is computationally good when compared with LOG. So these are the types of derivatives we can use to deduct the edges. Now, selection of scaling is very important. You see, in Gaussian formula, we are having sigma value, right? So if the sigma value is small, I can deduct fine edges. If the sigma value is large, I may not get exact fine details. I'll get only the coarse and blurred edges. Now see this image. If B and C, it represents the finer details. So finer details means small sigma. The small sigma represents somewhat noisy image. You could see this, right? So this is the original image. After applying the Gaussian filter, only I have applied smoothing, right? So after applying this Gaussian filter with small sigma value, I get the edges, but it has more noise. When you apply with a larger sigma value, the noises are not that much, but you get only the coarse detail. The exact cuts of the mannequin are missed here. Now, after smoothing with small or large, I'm going to apply the first order derivative as well as second order derivative. This is the result of first order derivative. This is the result of second order derivative. So I'm going to combine both to produce the final better result. Next, the process is color deduction. The traditional edge detectors works only on grayscale. Now we will focus on colored images. The colored images are usually represented as RGB. I'm applying the normal grayscale detector on each separate color channel, red channel, green channel, blue channel, that is known as band wise reduction. I'm going to divide as red band, green band and blue band and following the applying the same one. And orientation energy approach means it is very sensitive to orientation. Orientation in the sense it focus on direction. The edge may be slightly different. So in case of original image, if you find this edge, but after applying the edge reduction, the edges may be somewhat varied. The direction is known as orientation. It is very sensitive to orientation. The orientation will be exactly captured in case of orientation energy approach. The next one is color statistics approach. If you have multiple colors, we will represent all those colors in a histogram and I can compare the distributions. Next, combining edge feature cues. Human eyes are very good in detecting, are very good in combining brightness, colors as well as textures. Consider this, but machine learning algorithm should also do that. Let us see this. Here, this is the original image. The last one represents the human founded boundary detector. If you give this image to the human to identify only the edges or boundaries, they'll draw like this. That is a final image. But now I'm going to apply multiple gradients to detect the edge. So here this is a brightness gradient. Brightness gradient means it will only focus on the bright colors. Only the bright color edges would be represented. Okay, hope you see this. Only the bright colors are there. Now you could consider this image which is much better. Okay, this black color is much dark. So and there is a much color difference between this. So it is represented like this. Next one is C. C represents color gradient. If you have bright color, the edges would be much great, right? So here see this, the entire image is looking like the same, so there is no much changes in this fourth image. See this, there is a bright color like red. I could see much better edges when compared to this fourth image. The last one is texture gradient. Texture gradient means every features will be considered better. See this image, the human eye, human nose, human lips are considered better when compared to color as well as brightness gradient. BG, CG, TG, and combining of all this gradient results in this. Okay, so you could see all these three combined to produce this, but that is not that much better when compared to the human detected boundaries. So in this way, I can detect the edges. So these are all the strategies we have followed in edge linking. After detecting the edges, we have to link them to make it as a continuous contour. So connecting of edges is known as contour. Linking process, we start from edges. That is known as, I'll tell you. So I have detected so and so edges in my image. So these are my edges. I need to link that the edge pixel of every edge is known as edge. Okay, I'm going to connect all these end of the edge. Okay, that is known as start with the edge pixel and follow the neighbors in both direction. if the edges are from crossing zero crossings. In the Laplacian of Gaussian, I have said, right? So if there is a sign change from positive to negative or negative to positive, that is surely an edge. I have to link them. Okay, so the after linking the edge, some edge may be very light, some edge may be very strong. I could find very light line or else the dark line. Okay, I can use threshold formula to keep the strong edges, and the weaker edges can be removed. If the threshold is so and so high, then I can consider that edge, or else I can omit the edge. Next, we are going to use the chain code representation. Chain code means here the eight directions are mentioned: north, northeast, east, southeast, south, southwest, west, and northwest. I'm going to provide code for every cities or every directions: 0, 1, 2, 3, 4, 5, 6, 7, 0 to 8. So the 1 to 8, 8 directions are there. I'm going to number from 0 to 7. If I found an edge in this direction, I will consider as north and I will provide the number 0. If the edge is like this, I'll give the number as 1, it is northeast. Again, if the third edge is like this, I'll consider it as north and 0. So for every north means it will like this, west means it is like this. So similarly, we'll have north, west, south and east and northeast. So many directions are there, right? So after detecting the edge, we'll compare with this direction and we are providing the number, and on connecting this we'll find the complete edge. Okay, complete edge of an image. Next one is arc length parameterization. This is the connected or identified arc. Yeah, if you want to process only the upper part of the image, I can represent only the upper part in one curve, and if you want to process only the lower part, I can convert it to the only the lower part. So if you don't want to process the entire image, you can consider into two arcs or three arcs. There is known as arc length parameterization. Smoothing curves. This one is without smoothing. After applying the smoothing, the results are much better. Okay. So this is the final conclusion. A and D are original image. B and E are detected edges. B and D are detected edges. So you could see the exact representation of each images, right? So this white lines or represents the unwanted light. This can be removed. Okay, this flashlight can be removed. Here also the some white lines are represented. After removing this line, if you connect this, you can get a original image. So that's all about edges, edge link as well as edge detection. Thank you.